call on the actual event. So today we have 3 speakers, who each of them will be talking for 15 minutes. So in the first instance, what we're going to do is have Jeffrey give a talk. Now, for those people who don't know Jeffrey recently graduated from Master of Science in Mathematics and Statistics at the University of Melbourne. He received a Dwight Prize as the best performing student in statistics. He's currently working as a research assistant in Davis McCarthy Statistical Bioinformatics Group at the St. Vincent Institute of Medical Research. Before studying his master's degree, he completed a Bachelor of Science also at the University of Melbourne and worked as a graduate at the Australian Institute of Health and Welfare in Australian Public Service. So he's going to be talking to us about his RATAR package. And the floor is yours, except for Damien. How do I do that now? Behind me. This one. Thanks a lot, Damien. That is much better. Okay. So. You do the full screen.
I do the full screen, I think. I do indeed.
I think we do view.
This one? Or...
Okay, excellent.
Is that all right? Oh,
Floor is
excellent.
yours. Please welcome Jeff.
Hey, thanks very much to the South Side of Victoria for firstly having the award and giving me the award and giving me the opportunity to talk about the thing which won the award. So thanks for all of that. I hope everyone can see my screen and hear me all right at home. Just put anything in the chat if you can't. Okay, so today I'm going to be talking about RATAR, my R package for statistical models of repeated categorical rating data. So this is joint work with Dr. Damian Vukovic, Professor Lal Gurun, and Kate Tsang. Damian and Kate are actually in the audience tonight. All 3 have contributed to a marginalisation efficiency project, as well as me, which I'll touch on briefly at the end of this talk. And Damian and Lal also, they're the main contributors to RATAR, along with me. Okay, so RATAR was motivated by a particular data set, one instance of which you can see on the slide here. So this is actually an image of a skin cast taken from the back of a child's hand. Don't worry, the child's skin is not actually green. I'm reliably informed this is an artifact of the casting and imaging process. So this data was collected by researchers at the University of Melbourne who were interested in the link between type 1 diabetes and sun exposure in small children. Now, sun exposure is a pretty difficult thing to measure. You know, you might ask someone, how much sun exposure have you had? And sort of hard to know how to respond to that. So the researchers opted to look at the children's skin to measure sun exposure, and in particular to take these images. One difficulty of this, however, is that it's pretty difficult to feed an image into a conventional statistical model. Really, we would like to summarize this in a sort of number that represents the amount of sun exposure, which we can then, perform all of our normal statistical analysis on. To do this summarization, the researchers used an expert rating based on a classification scheme. So the idea here is to come up with a scheme which basically talks about the features of an image and then assigns them into different grades depending on the features of the image. And the grades here correspond to the amount of sun exposure, so 1 being the least and 6 being the most. So with this classification scheme in hand, what we need to do is take each item and assign it actually into one of 5 or possibly 6 categories. And this is done by a series of experts who know a bit about the topic and have read the classification scheme. The issue with this data is what you can see on the bottom of the slide here. So we have 5 raters for a particular image. This is just an example. And here raters 1 through 3 think this is grade 1, but raters 4 and 5 think this is grade 2 and 3 respectively. So there's a bit of consternation about what grade we should assign this image as. And so this motivates our need to really go in and model this data. And in particular, we really want to answer 2 questions. Firstly, what is the true class of the image? And more sophisticatedly, how uncertain should we be about the true class we assign? And secondly, how accurate are the rate? Oh, there are 7 things in chat. Is that because they can't hear it, or all good? Okay, great. Sorry. And secondly, how accurate are the raters? Which, we want to know, is rater 1 worth the same as rater 5? Is the undergraduate we got to, rate some images? Are they performing terribly, or are they all right? These sort of things. So this is probably a subsidiary interest in most cases, but may indeed be a primary interest in some scenarios. So originally Damien in 2018 got this data, was going to analyze it, and he looked through the literature to find an appropriate statistical model, because clearly we're a long way away from sort of regression or standard things. We need something a bit more bespoke. And he found this paper by Darwood and Skene from 1979, where this paper introduces a particular model of this data, which has since been called the Darwood and Skene model for obvious reasons. And this basically is a really good model to think about this type of data. The model has two key features. I'm not going to go through all the maths today, but it posits that there exists a discrete latent class for each item, a sort of true latent class for each item. And this allows us to do inference on things like the probability that a particular item is a particular class, which in turn allows us to sort of reason about the uncertainty in the predictions for the latent class. But the particular sort of calling card, I guess, of the Darwin-Skene model is this idea of parameterizing the performance of the raters as an error matrix. And we can see one of these visualized by rater, actually, my R package, on the bottom of this slide. So in this heat map, on the x-axis, we have a rating, sort of the rating delivered for each item. On the y-axis, we have the latent class. And each of these is then the probability that given the latent class, so given it is truly of class 1, say, the probability that we rate a particular rater rates in each of the categories. So the fact that this matrix has very strong on diagonal, we can see there, basically says that this rater is performing well. When we have true class X with high probability, they rate with true class X. And so this sort of error matrix idea is one of the key features of the Darwin-Skene model, and is a really good way of thinking about this data. Now, so Damien had found this this model, and he went, excellent, we're gonna fit this model to data, we'll all be done in a week. And he looked on CRAN and for an R package to implement it, and he found that surprisingly there are actually no R packages which fit the Darwin-Skene model. Allow us to fit the Darwin-Skene model to data, which clearly really reduces its usefulness and means we can't just fit it to data as we would like. So this is where Rater and in fact I come in. So Rater is an R package which fits variants of the Darwin-Skene model to this repeated categorical rating data. It has an obligatory hex sticker, it's on GitHub, it's on CRAN, and we have a manuscript describing it up on arXiv, which unfortunately recently got rejected after review at the Journal of Statistical Software, but that's a story for another day. So what functionality does the package have? Well, as I've said, basically it implements a very simple interface to the Darwood and Skene model and some variations. We can load the package, run the rater function to fit it to data, extract point estimates, posterior intervals, posterior samples, and plot various features of the model. And as you may have ascertained from these sort of language here, we actually fit a Bayesian variance of the Darwin-Skene model for various sort of technical reasons. To do this, we use the probabilistic programming language Stan, which is one of the sort of leading engines of Bayesian inference available today. So there are many features of the package. I'm going to highlight 3 in the next 3 slides. Firstly, it supports many data formats. So we realized as we looked at more and more of this data that the data can be long, it can be wide with grouping, and the package can natively take in data in all these formats to run inference on. We also implement not just the Darwin-Skene model proposed in the paper I showed earlier, but a variety of more recent variants. So things like a hierarchical Darwin-Skene model, class conditional Darwin-Skene model, homogeneous Darwin-Skene model, all slight twists on this formula, and we implement them all in the package. We also implement a technique of data summarization. So we realized that for data that comes in the wide grouped format I showed earlier, that we can actually rewrite the likelihood, dramatically reducing the number of computations we need to do. So we implement this in the package. And this can mean that certain data sets in a wide format, they would take hours and hours, possibly days to run the basic computations. With this optimization, it takes seconds. So for certain data sets, this has a really big impact on performance. Now, one problem with Stan in general, beyond this package or this work, is that it cannot natively handle discrete parameters. So we can't write in our Stan model, X has a categorical or other discrete distribution. Of course, however, we can fit models with discrete parameters. We simply need to marginalize them out of the model and then use the software to fit a marginalized model and then recover it. So this process is a little technical, there's a bit of math involved. So when we first started to work on Rater, I actually was able to find some sort of code people had used, pre-existing code, and we implement the model and get the package off the ground. But when it came time to write the manuscript, we really wanted to make sure we really understood what was happening in the marginalization, in the marginalization we were doing. And we had these sort of hilarious Zoom calls in 2020 when we were first starting to write the manuscript, where we would try to explain what we were doing to each other. And basically, we didn't understand what anyone else said. So we thought we really need to work on this marginalization and really try to understand it to write about in the paper, because it's quite confusing and something that hasn't been described well elsewhere. So this is actually a section of the manuscript. In fact, this section goes on for several pages, but we give quite a useful, I think, account of marginalization in STAN, which is of general interest beyond the Darwinskian model. In fact, we like this question of marginalization so much that beyond RATER, it's actually led to other projects. So we became very interested in the question of whether marginalization, this technique, actually leads to more efficient inference than, say, Gibbs sampling, where marginalization is not needed. And for this purpose, we recruited an excellent summer student, Kate Zhang, who's also in the audience tonight. And she has done amazing work on this project, investigating the efficiency of marginalization, which is now also a manuscript up on arXiv, and really gone into the detail to look at particular models and see what impact marginalization has. So this is a bit beyond RATER per se, but it's really an instance where our work on RATER has led to a need to understand the methodology in more detail and led to, I think, some really interesting work. Very briefly, I would encourage you to read the manuscript if you're interested. We find the marginalization has mixed effects in different scenarios, but the STAN, which does require marginalization, is almost always more efficient in our comparison. So that really highlights that sometimes marginalization may be necessary. So in conclusion, the Darwinskian model provides a really good way of thinking about this repeated categorical rating data, and the paper describing it is excellent despite the age. It's a really fantastic paper. If you would like to fit the Darwinskian models to data, I would highly encourage you to use RATER. In fact, you don't really have a choice. RATER is the only thing that implements it, but in my opinion, it's pretty good. So use RATER, and please, if you do want to use RATER, get in touch with any questions, queries, or concerns. If you're interested in the details of RATER, anything I've talked about today, marginalization, please read our manuscript. And if you're interested in the efficiency of marginalization, please read our other manuscript. And with that, I'd just like to thank all my collaborators and mentors in this work, and also Professor Anne-Louise Ponsby, who actually generated the Skincast data, which motivated this whole winding exploration. And with that, these are some relevant links. Thank you very much for your attention. Any questions now or questions at the end?
Yeah, okay. 5 minutes actually.
Oh, it's very quick. That's a shame. Oh, well, better to be too fast than too slow, eh? Anyone have any questions?
So, couple of comments from online. So, Guy says that our journal is not relevant.
Yes, I think we're going to go to Joss first, but our journal is definitely something we've looked at. Yeah. Okay, right. Okay. Good to know. Thanks for that.
Otherwise, everyone is creating your
That's not, we need questions.
Yeah. So what was the hardest part of creating the interface to RATER?
Oh, I would take a step back from that question if I can, Nick, and say creating the interface was really hard. I mean, it seems once you've done all this, you've written all this code and you've done all this Bayesian inference, designing the interface should be simple, right? But it wasn't. It was, we went back and forth, and we originally had a much more complex interface. So I think personally for me, killing my darlings, to use an expression from a writing, and taking out all the things I thought were clever, and taking a lot of Damien's advice actually, and making it simpler was a hard lesson to learn, which ultimately has significantly improved the interface of the package. So I would say, yeah, taking out the clever stuff, making it boring, but far more usable would be the hardest thing. Yeah.
Any questions or inputs? If not, I have one.
No.
So my question is to do with what happens if you have like an incomplete or missing data. So is the case that like if you have like a second rater who doesn't rate the second one, like does that cause issue?
It does cause issues, but so I didn't actually touch on that in the talk, but we explicitly anticipated that scenario because it does come up a lot, right? Yeah. You have these raters, they might be like doctors, they can't be there all the time, they have incomplete ratings. So the package can definitely handle incomplete, you can pass in incomplete data and it will do everything happily, where we're completely, yeah, it will definitely work in that scenario. Yeah.
Any other questions? Go ahead.
Yeah.
Okay, So we're gonna move on.
Great.
So
Thanks so much.
thank you to Jeffrey. So next is Shani. So I'll just introduce you, Shani. Do you want to set up? So next we have Shani, who's a statistician. She just finished her PhD at the Department of Econometrics and Business Statistics at Monash University. She's currently working as a research fellow with Professor Rob Hyman and Professor Dai Cook. Previously, she's done her master's and honors in statistics back in India, where she worked as a consultant and senior analyst in firms like KPMG and American Express. Her research includes visualization, computational statistics, time series forecasting, and data analysis. She enjoys using statistics to solve real-world problems and almost uses art always to do that. Now, the floor is yours, Shani.
Thank you, Emmy.
Please welcome Shani.
Thank you, everyone. Today, I'm going to present my R package Gravitas, which stands for Granularity Visualization for Time Series Analysis. Thanks to SSA Victoria and also the jury for the honorable mention for the Dai Cook Award. I am very happy to present my work here. Thanks, Emmy. Yes, so I understand that today, like now is the end of the day for everyone. So I have tried to, you know, have my presentation in the why, what, and how of my work, and keep it to point so that the takeaway messages can at least be the why and what of what I'm doing, if not the entire how. The how has, however, got two parts: the methodology that we have developed during the PhD, and how I can use the package for which you can see the hex star here. How can I use the package to do the work? So I will be walking you through more of that, how I can use the package today. And for if you want to know more about the details of the methodology, these are the two papers that you can refer to. One of the papers published with JCGS, the other one is on arXiv. All right. So let us start with the why of the presentation. So let us look at this in our energy demand data that I had when I started my PhD. So each of the lines that you can see here represent the energy demand data for one household. I have taken the energy data for 50 sampled households. What you can see here is it's available at a very fine temporal resolution for every 30 minutes, and they were available from 2012 to 2014. However, as you can see that there were many missing observations, as well as since there were many measurements, because it was 30 minutes for every for a 2-year period. So there were many measurements. So if I represent time in this manner in a linear fashion, a lot of measurements get squeezed in this linear view. And also other characteristics of the data being that they have got different start and end date. They have not been recorded for the same period of time. And also unequal length, right? So this is the kind of data that I was looking at. You might expect that any electricity data would have some kind of weekly, daily, and annual pattern. But what you can see here, if I represent time in this linear fashion, none of those behaviors can be interpreted well through this representation. There should be some representation which will allow us to visualize or analyze this repetitive behavior of electricity demand data, because it is important, for example, for energy companies to know more about the repetitive behaviors of customers to have more energy efficient for more energy efficiency, as well as some patterns, repetitive patterns that is not for electricity data, but there might be other patterns, like if you want to see like half hour of the day or week of the month, that might be important for some context. So it is important for them also to know these kind of repetitive behavior, so that they can customize their customize it for the individual or the group behaving similarly. So what we try to do here, now I come to the why of the presentation. So what we wanted to do was provide, so it was important for us to provide methods to better understand the patterns of these sorts of large quantities of time series data that are observed more than once per year. So I have given some more examples, although the motivation came from the smart meter data, the energy demand data. It can also be potentially be applied to pedestrian movement data or bike rides data, and more broadly, even for temporal data that are observed across years, decades, like astronomical data or non-temporal data. So this was quite surprising to us when we were building the application, that it can also be applied to non-temporal data, which has a hierarchical nested structure similar to time. So actually now I come to the what of the presentation. So which is what we did to address this problem is we try to visualize the probability distributions to explore these large quantities of temporal data across time deconstructions that can help us find underlying patterns in behavior. So there are two key terms here, like looking at the probability distributions and also looking at time deconstructions that can help find us repetitive patterns. So, so I showed you that if you represent time in a linear fashion from past to present, you can't understand this repetitive pattern. So what we came up with was this cyclic granularities, for example, hour of the day, day of the month, hour of the week, and so on and so forth, so that you can understand the repetitive patterns in the behavior. And why probability distribution? Because when you are looking at this, the first plot, where each time point actually corresponds to unique measurement, when you come from a linear world to this cyclic world where you are looking at hour of the day, so there are 24 categories from first hour of the day to 24th hour of the day. Each hour of the day would correspond to many observations, right? And I have shown you the characteristics of the data, that they might have unequal observations, they might have missing observations. So looking at probability distribution not only helps us to resolve that, but also since each category actually corresponds to many observations, looking at the distribution of the measured variable in this format is useful. So now I will directly go to the how part of what we have done. So the package Gravitas, it has some different components. So the first component is computing and searching. So cyclic granularities, it is important that we are able to compute all these cyclic granularities easily. So that forms the first part, the first paper actually, and it can be done through the create gran function. And then it is also, because it is not restricted to hour of the day of the week granularities, it is also important for us to know what are the exhaustive set of granularities that you should look at in a particular context. So that you can do through search gran. Now you will have a lot of granularities to look at, but then thankfully there you will not be able to effectively view all of those and analyze it, because all of the granularities are not compatible with each other to provide us some analysis out of the So this is the first part, is like refining the search using search gran that we got, and getting a fewer number of granularities that could be useful. The third part is inference, which is the second paper, and that's a development because that's not totally integrated in Gravitas package yet, not on the current version of CRAN, but it's on GitHub. So what it does, it refines the search further to select and rank only those granularities which has some significant patterns to it, because all the granularities would not be important to look at. And finally, after you found out the interesting granularities, then you can use all the functions under visualization to plot it to see if the distributions you are plotting has enough observations or not, using GranObs, or if you want to have any recommendations on the feasibility, using GranAdvice, that what is the distribution plot that you're using, or cross tabulation of the number of observations for these granularities. So I will not get time to go into the methodology, as I already said, but there is something that it is a part of methodology that I quickly want to go through before I go to the package usage. This corresponds to this section, which is the list of harmonies, refining the search for harmonies. So what I found was, when I was looking at different pair of cyclic granularities together, I found that, okay, not all granularities are compatible with each other for exploratory data analysis. So there would be many empty sets, because of which we will not be able to compare it across facets. For example, I've plotted day of the year and month of the year, and since each day of the year does not correspond to all the month of the year, this kind of cyclic granularities plotted together is pretty ineffective. Whereas you can see here, where I've done day of the week and month of the year, then you can see that each day of the week would correspond to months of the year, and so there will be no empty sets. So all of these kinds of sets are harmonies, but not necessarily they would have some interesting patterns. So that's why this inference part is also important. Okay, finally, just to make it a little fun, I have taken the cricket example, which is a non-temporal data that I have taken. So the Gravitas package has the cricket data set, which actually has the ball-by-ball data for Indian Premier League. So I'll not have enough time to talk about what the cricket sport is about, but I'm hoping some of you would already know it. In cricket, what we have is each ball, so each over consists of around 6 balls, each innings consist of 20 overs, and matches would consist of 2 innings, and so on and so forth. It's similar to time, where hour is nested within days, days within weeks, weeks within months, and so on and so forth. So if you imagine each ball to be an index that actually records the progression of the game, then you can understand that a ball is nested within over within innings, and innings within match. So we have got a hierarchy table correspond to cricket. Now what we can do is have the data structure. So the Gravitas package takes Sybil as an input. So after you've got cricket Sybil, then you can use the function search gran to understand what are the granularities that you can look at. So we have got 6. Now if you want to plot 2 granularities at the same time, one on the x-axis and one on the facet, you can have 6 permutation 2, which is 30 pair of granularities to look at. And that would mean 30 plots to look at and then analyze, which are far too many. So what you can do is look at the set of harmonies and using the function harmony. And what you find is you have just got 7 harmonies out of the 30 visualizations that you had originally that you had to look at. And plotting the 23 pairs are not important because they would lead to empty combinations and you can't compare. Then you can use GranAdvice to see some kind of recommendations like what is the distribution plot that you should be looking at, if they are homogeneous across facets and within facets or not, or also some cross tabulation. And finally, if you're happy with the set of harmonies, then you can plot them using the function probplot. So I would want to explain this example. Here, what I have done is plot the balls of the over of the innings on the x-axis and innings on each facet. And I have used probplot to do that. and a letter value plot. So what we can see here is when the team is in their first innings, there is a mounting pressure on them to score higher as they reach towards the end of the innings, right? So there is an upward trend in the distribution, whereas such a trend is not there in the second innings. Which means that since in the second innings they already have a target that they want to aim for, they are under no added pressure to like score high and get more runs at the end of the innings. So this kind of insights can come through these methods, and you can find other examples in the paper. So just to summarize what I've been saying and to come back to the benefits of using these methods, I came back to the energy demand data. So here I have plotted the energy demand data for 8 households. And so you can see here that you can see some repetitive patterns, but you can't see that how the repetitive patterns are different between the different households, and also which ones are significant at all and which one I should be looking at and how they're different from each other. So there are different kind of summary plots that you can finally produce after using Gravitas package that can give you insights about this kind of repetitive behavior. For example, you can see that ID5 has some kind of repetitive behavior, but none of it is significant. So significance is given by the asterisk here. So none of these periodic patterns are significant according to household 5. So their behavior is quite sporadic. Whereas ID7 and 8, they have, so you can see that ID8 is not maybe in their house after September 16th or something, but they have got very similar periodic patterns. So it is not important that they need to have similar total usage or something. If they have the same periodic behavior, that can come out of these kind of summarization. So I think I am out of time. Yeah, so to know more about the package, you can visit the GitHub, and the slides and the codes are here. And this is a joint work with my thesis supervisors, Dai Cook and Rob Hyman.
Okay, so I have one quick one. So you know how for the cricket data, there is a hierarchy among the matches. So like, how are you encoding the hierarchy when you do that? Because you have to let it know somehow.
Yeah, so you can put this as an input in this Surge grant. Yeah. Okay. So yeah, so for any context, if you have this kind of a hierarchy table, you can put it as an input in the package.
All right, and you don't have any questions? People just praising you. Well, thank you very much, Shani.
Thank you.
So not the last, or the last actually, but not the least, we have next Patrick. Now, Patrick, would you like to just come and set yourself up here while I? Yeah. So Patrick is a second-year PhD student at the Department of Econometrics and Business Statistics in Monash University. He is, in fact, a student who is doing automated visual inference using computer vision model with Professor Dai Cook and actually myself. His research interests are machine learning, computer vision, data visualization, and statistical software development. And I know that he is Dai and our student, but I would like to just emphasize that we had nothing to do with who won Dai Cook Award. Like, it was purely external reviewers, and so I know it doesn't look nice, but it just so happened to be like that. So please welcome Patrick.
Hello everyone, I'm Patrick Nee from Monash University. And today I wanted to present the work Spotteroo, which is an R package. Spotteroo stands for Spatial Temporal Clustering in R of hotspot data. And it's a work that I've been developed in my honors degree. And it's being packaged into our package in last year. So the motivations of this package or the algorithm or the clustering algorithm is the 2019 to 2020 Australian bushfire season, and is an unprecedented disaster which have more devastating impact on the environment and the property than the other bushfires in the history of Australia. So when I was doing the honors degree, I took a research project that aims to find the causes of bushfire. And what was the issue was we found that we have there's a lack of information of when and where the bushfire was started. So it's very hard to investigate the cause of the bushfire because we don't know when and where it started. So and then we find that we could actually use the remote sensing data, or with so-called remote settlement data, to give us the information of the locations and the time of the bushfire emissions. But the hotspot data or the remote sensing data is very noisy. So sometimes those hotspot data are actually not caused by bushfire. They may be caused by other events, for example, like structural fire. And some fires are actually corresponding to multiple hotspots here. So if that, for example, the one that we use in the research, that the JXA Hammurabi A satellite Wi-Fi product that has 0.02 degree of spatial grid resolutions and 10 minutes temporal resolutions. If one fire that lasts longer than 10 minutes and if it was spread further than 2 kilometers, then it would corresponding to multiple hotspots in the data. So it means that we have to have a way to group the hotspot data into fires or into clusters, such that we can know the first instance of the hotspot. Then we could say that, okay, that's where the fire started or when the fire started. And talking about the Spotteroo author, the authors of Spotteroo, that package is developed during my honors degree, and Professor Daituk and Emily from AT&T are my supervisors. And you can install it from CRAN, and it just calls Spotteroo, SPOTORO. Let's briefly talk about how that algorithm actually works. So first thing we do in the algorithm is we divide the hotspot into intervals. So the first parameter we define is the active time. That is to specify the maximum amount of time a fire may stay smoldering but undetectable by satellite before firing it up again. So why do we need this parameter? It's because when we look at the hotspot data, sometimes you find that if there's some cloud cover, then a hotspot may disappear from the sensor, and then it may appears again 10 or 20 minutes later. So the algorithm has to take into account that behavior. So we define this active time parameter, and then we divide those hotspots into intervals. As you can see, those intervals are kind of overlapping with each other. The first interval is, it contains all the hotspots from hour 1 to hour 1, which means that the first hour hotspot will be included in the first interval. And the second interval includes all the hotspots in the first hour and the second hour, and so on. So in general, the equation can be summarized as the left-hand side is a maximum of 1 or t minus active time, and the right-hand side is t. So this equation makes sure that it starts from a positive number. It starts from 1 at least, and the length of that interval is not longer than the parameter we define, the active time. And after we define this interval, we first do a local clustering, we call it, that just only doing the clustering spatially within each of the interval. So if any of those points are within the distance the second parameter we define, the adjacency distance, if it's within the adjacency distance, we connect them to each other, like this one here. Here's the hotspots in the ST, so it's the T interval, and then we connect them to with each other if they are within that distance. And then we form a graph, and every connected component of that graph will be considered as an individual cluster. So for example, now in that graph, there will be 4 clusters there. And after we do this clustering within each of the time interval, we will have T clustering result. So we have to combine those T clustering result into a final result. So we did that by updating the membership iteratively. So for example, now when we're dealing with ST, this may not be that clear in this monitor, but when we have ST, for example, if we have this red dots here representing the hotspot in ST, we got this convex polygon here representing there are 3 clusters in ST. And then we also consider that some of those hotspots has already been clustered in ST-1. So because we have some overlapping time intervals there, so some of the hotspots will have already got membership. And we could just adopt those membership into ST. So we got those numbers here, 1, 2, 3, 4. And the remaining points is in red, it's drawn in red. What we need to do is to update the membership for those red dots. So if the red dots and the label share the same polygon, so if they are in the same cluster, and then the red dot will find the nearest label to become the updated membership. So for example here, now these red dots are more it's closer to 2, so it's being labeled as 2 afterward. And then these red dots here are closer to the 4, and then being labeled as 4 after that. So after we updating the membership for each of the interval, so from time 1, from t equal to 1 to t equal to the final hour, and then we would collapse all those time interval into just one final clustering result. And the final step we do is we handle the noise in the clustering result, because we find there will be so many small cluster that only last for like 20 minutes, and then it's spread only like 1 kilometer or 2, not a real big fire. So we decide to choose these another 2 parameters there. One is for the minimum number of hotspots in a cluster, and there is another one is the minimum time of a cluster can exist, needs to be can exist and still be considered as a bushfire. So if any of those clusters doesn't meet these 2 requirements, it will be labeled as -1 to indicate the represent noise. And then this is the usage of the functions. That the core function is hotspot underscore cluster. Then you need to provide with a data frame or some kind of list. And then you define those parameters we just mentioned, the active time, adjacency distance, minimum points, minimum time. And this time unit and time step is for discretize your data. So for example, if we have a continuous time series that you want to put it into time index, like hour 1, hour 2, hour 3, you have to tell the function what kind of unit you want to choose and how large the time step you want to be. And when you run the function, it will give you a report to tell you the information, like how many times indexes found and how many cluster found, and how many, after handling the noise, how many cluster left, and it computes some little bit of summary statistic in the end. And also tell you how long it takes to compute that this many hotspots. And after you got the result, you could just use the summary function to get some summary statistic. It will tell you how many observations in the cluster, and the duration of the cluster, distance to the elision points, and the time from elision. So how long that fire lasts. And then it goes to the visualization of the cluster result, which I found is more intuitive when we're looking at the fires in the bushfire season. So for the first one, I just use the default function plot result here, and then I give a background map, which is happens to the vectorial map. And I choose a cluster 58, 83, 129, and 163. These 4 clusters, because those are the largest cluster in the result. So choose them. And on the right, you could on the left, this one is showing the spatial distributions of the cluster. And on the right-hand side, when I say that I want the movement by movement plot, then it will show me some moving average of the illusion point. So the central of the fire, how it moves. So such I know that if it's aligned with our lodgement, so aligned with our knowledge, if it happens to know the vegetation distributions or where is it in of that fire, you may know, you make a check that whether or not that fire movement coincide is aligned with your knowledge. And the final plot of the package is the timeline plot. This one is the it can show you the intensity of the fire, so intensity of the bushfire in the bushfire season. For example, now we can see that in the 2019 to 2020 bushfire season, most of the fires happens in the end of October to around March. So it's around November to March here. And it's showing that most of those fires last around 15 days. And in the bottom, there's a map for noise. So this is showing that how much of those hotspots being left out from the result. And if you find that, okay, like this one here, you find there's a high density of noise, it probably means that there's something in the data that we don't consider as cluster that we may to reconsider the parameterization. Like we need to choose another parameter for the minimum, like this parameter here. We may need to consider using a different parameterizations for the result. And that's it for my talk. And if you would like to check the actual implementations of the algorithm, you could, like there's a manuscript there that I have been submitted to our journal, but there's no response at the moment. Yeah.
Do you have any questions from the audience in person?
How do you choose the minimum points? I mean, you say that it was...
I didn't show it in this presentation because I thought it would be time consuming to talk about that. So basically we come up with a script plot type of visualization to see the noise proportion. So every time you choose a parameterization, it will give you the noise proportions of your result. So now here, 4.34%. So if you see the noise proportion is dropping down, it means that it's considering it's, so when you increase your adjacency distance or your minimum points, so it allows for if you increase the active time or adjacent distance, normally the noise proportion will drop down because you absorb more of those hotspots into your clusters. And it may not be a good thing, so you want to choose a balance point there. Now we did in PCA that we may want to choose a script like elbow point there to get the best parameterizations. Yeah.
I've got another one. So have you done like some validation on your, so you showed that you can validate that it is actually.
So just repeat the questions so people online can hear. So this question is about the validation, and it's also similar to the question I had, is like, how do you know when you do your clustering, like that actually corresponds to one particular set of fire? Like what's the step that you're actually using to do the training?
So that one is we actually manually check some of those fires. For example, in the Phillip Islands, there's a fire there. We check it whether or not it's being considered as an entire fire or being divided into multiple fires. And also, this is also very difficult because the definitions of a fire is not that clear. So how could you consider, is it a fire or two fires or three fires if they're spread around like that? So for us, we will consider if they are connected and we see some continuous behavior, see, for example, if it's like one fire spread to the other, I will consider them as a big fire.
So we have a question from online as well. So from Nick. So Patrick, I really appreciate the printing of output using CLE in your spotter room. And for those people who don't know, it's to do with these kind of nice outputs. It's a package. I was wondering, how did you find programming the interface using the CLE package? I find designing print methods can be quite hard sometimes. I'm curious what your experiences are.
Oh yeah, so I spent a lot of time to figure out how to use this kind of output in R. So the CLI package is fantastic, but it's not very easy to use. And as you can see that there's no coloring on this line here, but if you actually use it on your RStudio or something, or some terminal, you will find there's a coloring there. There's like this one is in yellow and that one is in blue, and it looks much better. Yes, just plain. So now it's probably because it's not using Unicode or something. I don't understand that for that part. But I found that when I use CLI, I need to carefully use those parameter like arguments in, for example, define the diff for a particular output. It's not very easy to use. Sometimes I will see some conflict there. I don't understand why it doesn't work. So I get some workaround with it.
Okay, well, my experience is different. I thought CLE was easy to use. And if you know HTML, like they do have a corresponding one, like for example, H1 corresponds to header 1. So like, I don't know.
I'm not a master in HTML.
That's not true. Patrick is very good. So I have a question, which is to that, this is an application to bushfires. Have you thought of, because this is an algorithm about clustering, can you think of like another potential application that might actually be useful as well?
So actually this one is very special, especially specialized in bushfire. We consider the behavior of bushfire such that we design such an algorithm. Otherwise, we could just use some existing algorithm to do our clustering. Actually, we have discussed that in our paper, that why do we need to develop a new algorithm just for clustering bushfire? So I guess it may be useful in other cases, but we may need to like reconsider whether or not some of the assumptions are true in the algorithm.
Well, thank you very much to Patrick, as well as Jeffrey and Shani for their great talks. Please give them a hand.